Hey, good evening, class. Welcome back. We'll give it a few more minutes to permit everyone to log in, and then we'll get started with the common emitter biasing and amplification fundamentals lab. All right, we're 3 minutes after the hour. Let's get started. So tonight you're starting the BJT biasing and amplification lab. This is going to be a 3-week lab. So tonight will be the kickoff night, the 19th. Next week is a holiday on the 26th. And then I believe we go till the 10th. I'll double check, but I'm pretty sure that we have 3 weeks left through the 10th before final set. Actually, I can come back. We'll check the syllabus really quick to verify that. Let's see here. Actually, I don't have dates on that. I'll double check that, but I'm pretty sure it's we have 3 remaining weeks for it. If not, we can wrap this lab up in 2 weeks. Let's see here. So going back to the lab, this is lab 6. It's the common emitter biasing lab. So for tonight, to kick things off, I'm just going to discuss the preliminary calculations and the SPICE simulations. Then 2 weeks from tonight, I will jump into the laboratory experiment part of it and discuss those steps. Let's see here. So for tonight, just go a couple of things on the preliminary calculations. You're going to be using figure 1 for both the hand calculations and the SPICE simulations. The default component values, 2 of the 3 are accurate, and I've got them indicated in a PowerPoint which one I'm going to switch out. The resistors provided in your kit, you have a 10K and you have a 1K. You do not have a 22K. So what we're going to do is we'll just change RBB, which you're only going to use anyways initially for the hand calculations and SPICE simulations, but we'll use a value of 20K on that one. VCC, you can simulate it at 10 volts. I recommend just doing 5 volts because, again, that's the limit of the analog discovery 2 device that you're going to be using. Then a couple other things. I'm sure, well, I should say, I guess, hopefully you picked up on this in class, but there's a couple assumptions that are going to be made in here. The first one is IC is approximately equal to IE. Well, why is that? Well, you have 2 different currents coming into your emitter right here, right? You got your collector current, and this is you can think of the emitter as like a summing point. Then you have the base current coming in. The base current is going to be significantly less than your collector current. So that's usually for hand calculations. A fairly reasonable approximation to start with is just to say that the emitter and the collector are equivalent. The other one is once you get to step 2, you start talking about beta. Beta is going to impact the ratio between your collector and your, well, it is the ratio between your collector and your base current. So you're going to be playing around with that in here. Then the other one, in terms of variability, when I say playing around, then the next one is temperature. So as you increase temperature, the voltage developed across this base emitter junction here, which you can just pretty much think of as a diode, right? It's just a PN junction is all it is going to be temperature dependent. So as you increase the temperature, and this ratio is given to you here, like supposedly, if you increase it by 40 degrees Celsius, how is VBE going to change? Well, they're telling you it's going down as temperature goes up. So we refer to that as the NTAT. So this is a negative temperature coefficient. So for every degree, it's going to change by -2 millivolts. So for 40 degrees, your VBE will be 80 millivolts lower. So why is that important? Well, if you're assuming the current stays the same through here, but temperature changes the VBE, it's going to have an impact on your base current as well, correct? So two of the things that you're looking at in this lab are what has the largest impact in terms of performance on your circuit. Is that shifts in beta? So you're going to be making some pretty big increases here, about 50 degrees. Or is it changes as a function of temperature? Excuse me. So keep that in mind as you go through these steps. So these are all the hand calculations working up through here. Then let's get to the SPICE simulations. So for SPICE, you're going to be using the 2N3904 component. I put this PowerPoint together. For some reason, it's not opening up. Let me see here. Here we go. Let me select it for some reason. Let me go back and see if I can pull it up from the lab site. So I've already got it posted right here. This is that 2N3904 BJT pinout. I'm going to add to this as we progress through this lab. Specifically for once you get to the measurements part of the circuit. Here we go. So the first thing I want to point out is what component you're going to be using. Granted, you're not going to be necessarily jumping into this tonight, but for some reason, if you want to work ahead and know what component to reference, you have two different BJTs in there. You have a 3904 and a 3906. So the 3904 is the NPN. That's the one you want to use in this lab. Then there's the 3906, which is the PNP, which we will not be using in this lab. I'll admit, like I had to really, unfortunately, the printing on these is really horrible, at least in the ones I got in my kit. Hopefully yours are better and they look something, let's see here if I could get a better example here. Hopefully yours looks something like this. It's a little bit easier for you to read and identify the components. For some reason, if not, I recommend using a magnifying glass or zooming in with your phone and taking a photo and identifying them. In my kit, they came in on this ribbon strip right here, and I had 5 of them ganged together. So if you can identify which one's which, go ahead and grab the correct one and pull that off. Now, for as far as pinout goes, this is, I didn't take a picture of the top down on this one, but what you'd see is a flat face on it with a curvature on the back, and that'll help you get the orientation right so you can identify which pin is you have 3 of them, right? So you got your emitter, base is in the middle, and collector. Beyond that, I also included in here a slight difference in terms of the component values that you're going to be using. So 10K and 1K, but for RBB, just use 20K. And I also included, we'll get to this in a minute, but this is what your SPICE schematic should look for, or the schematic for your SPICE simulations, just so you have a reference to work off of. So let's go back to the lab really quick. Let's see here. Click on this. There we go. So for your SPICE simulations, you're going to build up the circuit, figure 1, and also what I just showed to you. And I'll show you how to reference the component here in the middle. And you're going to set the DC value to the VBB calculated for your hand equations up above. And then you're going to record all these DC values for voltage and current at these various nodes in the circuit. If anything is significantly different than what you find in step 1, you're going to want to go back and verify the simulations correctly. And by there, you want to make sure that the component values are right. Then check your hand calculations because maybe you didn't bias the circuit correctly. Then the last thing I'd ask you to do in this step is record the value of beta. I will show that to you in a second as well, as far as how to do that. Once you complete step 5, you're going to go to step 6. This is where you're looking at variability as a function of beta. One thing I didn't point out previously, but beta, there is a lot of variability in it from device to device. So if you went out and bought say 100 of these 2N3904 BJTs, there would be quite a distribution in terms of variability of the beta spread on them. It's just a function of from manufacturing of the components, a variation in the doping implants on them. So that's going to be the first one. You're going to edit the SPICE model and change beta, record your results. Then you're going to go to step 7. You're going to put beta back to its original value. So you want to make note of that as you're doing this, right? What the original value is to put it back. Then you're going to change the temperature. I'll show you that as well in a second. Then the last thing you're going to do is you're going to perform a DC sweep of your bias voltage from 0 to 5 volts and obtain a plot of VC, VB, and VE. And you're just going to want to label the regions on that and understand, what the BJT amplifier is doing. So that'll conclude the first portion of this lab right here, just getting up through the simulations. I'll get in a laboratory experiment on the next video. So let's jump over to PSpice here. Pull up my remote desktop. And zoom in on this a little bit here. All right. So the first thing, I'm going to close this out just so I could walk you through every step. Let me get rid of this guy here. There we go. All right. So where do you get a 2N3904 BJT? You're going to want to go to place PSpice component, and you want to come down here and go to search. Click on search, and in this little window right here, you're going to want to type in the 2N3904, hit enter. And I realize my results already pulled up from the previous search that I did when I built the schematic up. But you're going to want to come in here to this first line item, double click it, and come out to the side here and drop that down. And that's going to be your BJT that you're going to start off with. I'm just going to delete this one since I've already got it on the schematic. After that, you're going to want to just build up the rest of your schematic, right? Just as you would in all of the previous labs. So place, part, or PSpice component, you got your PSpice ground, multiple resistors, then all you're really going to need is your voltage sources, which you could do DC voltage sources. Other than that, went in, I just named all the resistors to match the schematic, did the resistance values, and put voltages in here. Again, I recommend you do it at 5 volts. I did it at 10 volts just because that's what the lab was originally built up for. And also, I did the calculation by hand to come up with a base voltage in order to get me the right current, which for the first step, they want you to get half a half a milliamp, so 500 microamps for collector current. That's why I left it to you. If you want to do it at 5 volts, again, you're going to want to do a comparison between your simulation, your hand calculation, your simulation, and eventually when you build the circuit up and all the results. So I'd recommend doing it with a VCC at 5 volts. I did it just because I didn't want to give away what the base voltage was for your configuration. So once you got the schematic built up, you want to save it, as always. The next thing is you're going to go to your PSpice, new PSpice simulation. I'm just going to jump to edit because I've already set it up. And you're going to want to do a bias point simulation. Now, here's where things are a little bit different than what we've done in the past. We've just done a straight bias point, ran the simulation, and got the voltage and collector currents, right? Well, now you're going to want to do a save bias point. So the first time you run this, it's going to ask you to save the bias point information somewhere. So it's going to save this file. I just put it in the temp directory and named it BJT biasing. You can call it whatever you want, put it wherever you want. Just the key point is that you know where it's at and what it's named. So we'll hit apply on that. Let's see here. We're going to come back. Then the other thing you want to do, so that's under the save bias point settings, right? Now I'm coming back to the general settings, and you want to include this first option right here, which is include detailed bias point information for nonlinear controlled sources and semiconductors, .op. So what this is going to capture for you is the beta value of the transistor, transistor here. Okay, so that's what you're looking for in step 5. It's asking you to go in there and see what the beta value is. So I'm going to hit OK here and save that. Then I'm just going to go ahead and select the voltage and the current. You can see I already ran the simulation, and I got my current right about where it's supposed to be, right? It's close enough. So that's another thing too, as you're doing this. If it asks you for half a milliamp, 500 microamps, you don't have to get it perfectly right at 500. If you're like 495 or 505, you're pretty close. It's close enough within a margin of error, okay? So I ran the simulation. Then to look at the output value for this schematic, you want to come up to PSpice, and you're going to go to View Output File. So I'll leave that there for a second just so the video captures it. So you're going to go PSpice, View Output File. You're going to click on that. Then you're going to have this file open up here, which captured your bias point for your simulation. So you'll notice you'll come down through here. This is pretty much like the net list of your schematic. It's capturing all the different values. Then we're going to come down through here. Here's your BJT model parameters. So these are the parameters, much like the MOSFET lab, where you went in and manipulated them. This component already has a model file built up, so you don't have to do that. But you can come in here and see what the different model parameters are. For example, your beta, okay? But more importantly, what they're going to have you looking at in one of the steps is they tell you to look at the beta DC. So this is the beta value at DC, okay? So this one is 77.9. This is the one you're going to be looking at to see how it shifts when you start manipulating the beta value. So again, I just want to point out to you for these steps, when it asks you to go in and look at the small signal parameters and the model parameters, this is where you come in, and you got to look at this model file. And you can see here, I've looked at it multiple times. So that's kind of a good thing, right? So you can come through if you're keeping track of these, and you can do a bunch of simulations with changing the beta values, and you can come through here and see how it changes, you know, different parameters within the circuit. So to get back to the schematic, you just come back over here to page 1. So see the tab, page 1, click on that. That brings you back to your schematic. Okay, So now I'm going to show you how you change the beta value within the model itself. So just like the MOSFET, you're going to left click on the BJT, you're going to right click, and you're going to go to Edit PSpice Model. You're going to click on that. Nothing's going to pop up. You're going to have to come down here to the bottom on the toolbar, click on the model. You're going to want to enlarge that. Let's see if I can make the view a little bit better. This is horrible. Huh. Yeah, I'm not sure why it's scaling it so much on mine. Apologize for that. So hopefully you can see it. It's the second line is the BF value, okay? This is your maximum forward beta. The value is currently at 254.395, and the default value is 100. So if you wanted to change it, you just come in here and you click where the value is, and you could change this to, let's change it to 100, right? Since that's the default value. I'll hit enter. Then I'll come up here, go File, Save, hit OK. All right. And then I'm just going to minimize this. We'll come back to the schematic. We can see the voltages and currents right now. And I'll run the simulation again. And we got to go back to the schematic. And what you're going to see here is a significant shift in the DC parameters of the circuit, right? So previously I was like right at 5 volts almost, and my current was like 499 microamps. Now look at it. So I lowered beta. So, and what happened? Current went down and voltage went up. So in terms of the voltage and current, that's logical, right? So the more current you have going through your collector resistor, the bigger the voltage drop you're going to have across this resistor, and the smaller voltage you'll have on your collector. So the fact that the current went down, that should tell you there's a smaller voltage drop across this resistor and a bigger voltage here. So I point all this out because I think it's beneficial to think of things in terms of relationships, right? So what did we experience on this one? Is beta went down, and I cut it by more than half. I think the initial value was like 245, and the current went down with it. So that's probably the most important thing to remember. If you make a variable go one direction, see what the circuit does in terms of the parameter, which being collector current for this one, you're monitoring, see what direction it goes. Okay, so that is for the changing beta. I'm gonna go back and put this one back to the correct value. Now, I'll just change it to 245 for right now. Now, for some reason, if you lost track of the value, what you could do is just close out this model file here. You could come in here and delete Q1. Then you could just reinstantiate the device again and save it. And I'll show you, like, by rerunning the sim, see how it returns back to the original value? So it reset it back to the default parameters within the model card. So that's how you're going to change beta and observe, variation in terms of your DC performance of your circuit. Now for temperature, you're going to come up here and edit your simulation profile. And then you're going to come in and you're going to select, let's see here. Let's go back to this. I think options. Okay, here we go. So let me completely back out of that just so you can see how I got there. So you're going to go PSpice, edit simulation profile. You're going to be on bias point, general settings. You're going to come to options, and you're going to change the default nominal temperature. Okay. I'm going to change this to 85 degrees C. All right. I'm going to hit OK. So now we're increasing the temperature. Let's see what happens. So we're at 498 microamps. Go ahead and run the simulation. And now we're at 409. So it went down significantly, right? So now by significantly, you're going to want to quantify that in terms of your changes. I changed it by so many degrees C and the current change by so many microamps. And you're going to want to get like a percentage change or a value change. Then you're going to want to determine, and understand probably what has the bigger impact, either beta or temperature. Then you change temperature back, just go to PSpice, edit simulation profile, go to options, and put this back at 27 degrees C. So that's your nominal value, right? And just run it again. So now we're back where we're at. The other thing you could do if you want to do a sweep, which would be, you can come down here and click on temperature sweep. That was another way you could actually change the temperature instead of going to options. You could just come in here and say, run the temperature at 27 or 85 or -50. So there's a couple different ways, right? Let's see here. Or you could repeat the simulation at a bunch of values here. That's another option too, if you want to do multiple points. Let's see. So that's one way. If you want to do a sweep, you could select DC sweep. Now again, I'm going beyond like what the lab's asking you to do. They're just having you go step by step, right? Bias point, change a value, record it. But if you wanted to, you could do a DC sweep, come down here, select temperature, and you could go from like, we'll say -50 to 85 and 1 degree Celsius increments. Then we could put a, let's do a current. I think current is more appropriate for the BJT to look at. Then we'll run that. You got to come down here and click on the blinking icon and see the plot. But now you can see that the change is a function of temperature, right? So usually 27 nominal is the temperature. So that's kind of interesting, right? Because it's right at the top of this peak here. And depending on what direction you go from nominal, it's possibly dropping. It's dropping off for this particular component, right? So close this out. I think that's about it. Yeah, that's enough information to cover as far as what needs to be done for the first 8 steps in this lab. I'm going to jump over now and see within the chat forum if there's any questions at this point. This will be your final lab that you'll be returning a report in for. So we'll talk about the report details on the next Zoom meeting. But as always, I'm going to ask that just document your hand calculations for the preliminary steps 1 through 4. Then for the SPICE simulations, I would say, document relevant data in terms of, you could take a screenshot of the DC bias point of the circuit, or you could comment on, I'd probably recommend commenting on like what your beta value is or your temperature value is for that particular setting, just for your own record so you can keep track. When will we have the past labs graded? I'm going to take care of that this weekend, Andrew. I'll have those results posted by the end of the weekend. The bottom line is if you submitted something in its entirety, you will get full credit for the lab. Any other questions? All right, if not, go ahead, get started on this lab. And if any questions pop up, feel free to post it on the Moodle board or shoot me an email, and I'll help you resolve it that way. All right, have a good weekend. Yeah, have a good week off too. Enjoy the holiday next week. A little downtime before finals come.